In the last video, I talked about how when there's a beam of electron hitting a piece of metal at a very high voltage, X-rays can be emitted and the wavelengths can be measured using a crystal as a diffraction grating. And this is the typical kind of spectrum that would be observed, a continuous background with a few sharp peaks. Now let's try and understand the features in this spectrum qualitatively. I'll go into more detail later and in the next video. Let's just ignore the peaks for now. Let's look at this continuous what we call the background. And if you look at this continuous background, apart from the fact that it looks smooth compared to the sharp peaks, it looks smooth and broad, there is also this very rather unusual feature that the curve just comes suddenly to a stop here and goes right down to zero. So let's try and understand these two features. The continuous background is actually due to what might be described as the breaking effect on the electrons, meaning that when this beam of high energy electrons hit the metal, there are lots of electrons in the metal, so the repulsion from the electrons in the metal, or if you like the collision of this beam with the metal, would cause these high energy electrons to slow down and stop. So the repulsion or the presence of the electrons in this metal will have a braking effect, in the sense that it would cause these incoming electrons to slow down. Now, a braking effect also means that the electrons in this beam would lose its kinetic energy. So since energy is conserved, it has to be converted to some other form, and in this case, it can be converted to X-ray. Right? And because the collision between the incoming electrons and the metal and the atoms in the metal plate is random, it is likely that some electrons would lose more energy, some would lose less energy, and therefore the X-ray photons emitted, some would have more energy, some would have less energy. And because it's all random, there's likely to be a whole range of energies that are lost, and therefore a whole range of X-ray photon energies that are produced. And that explains why we have this smooth part of the spectrum here. Right? It's due to the random collision, which results in the incoming energy losing a range of different frequencies. But if we are talking about say 1,000 volt electron, then it refers to a particular energy. It refers to a particular energy of the incoming electron. So the most that it can lose would be all of its energy, which would be 1,000 eV, 1,000 electron volts of energy. So it can't lose more than 1,000 electron volts of energy. Okay. So if you think about this, the energy is related to the frequency of the X-ray by HF. That's the photon formula, photon energy formula. So the maximum energy in this example is 1000 volts. So E is at most 1000 EV. That would be the maximum kinetic energy. Okay, so that means that there would be a maximum frequency. There would be a maximum frequency, and that would correspond to a minimum wavelength. A minimum wavelength. Right, because we know that C is equal to F lambda. So if F is big, lambda is small. So that's why there's a very sharp cutoff here, because we don't get X-ray photons with energies more than the energy of the incoming electron. Okay, so there can be no spectrum below this wavelength. So that explains this continuous spectrum. It's due to the breaking effect on the electrons. Now about the sharp peaks. Now qualitatively, the sharp peaks are due to transitions from the different shells in the metal atom, in the atom here, in the atoms of this metal plate. So let's say we think about it like the hydrogen atom, which enjoyed like Bohr would have drawn it, like the Bohr model for the hydrogen atom. Then there are only a certain allowed radius for the orbits. Okay, let's say we're talking about the molybdenum metal. So the peaks here, right, after years of study by people, this peak, this biggest one, has been found due to a transition from the second orbit to the first orbit. Okay, that one here. And this is often called the K alpha line. Okay, where K is also the name given to the first orbit. In the hydrogen atom, we call it n equals to 1. But in X-ray spectrum, it's common to call this innermost orbit the K orbits. And the next line here, with a slightly lower wavelength, corresponds to the transition from the third orbital down to the first orbital. So that will give us higher energy photon. Okay, and that line is often called the K beta line. So both these lines are transitions from high orbits to the innermost orbits. Now, the next two lines have longer wavelengths and tends to be lower, weaker. And this corresponds to transitions from, say, the higher orbits to the second shell. And the second shell is called the L shell in X-ray spectrum. So these lines here, that one is called L alpha. So let me just backtrack to the K alpha. So the alpha refers to the transition, to this transition. Beta refers to that transition. So for the L alpha, it refers to the transition from the third to the second, third to the second shell, and the next one is called L beta and refers to the transition from, let's see, 1, 2, 3, from the fourth shell to the second shell. So that's L beta. And so that's the fourth shell here that we need to think about. Okay, so in a very similar way to the hydrogen spectrum, These lines correspond to transitions from a higher orbit to a lower orbit.